A 99% of walking is falling forward, perfectly caught. This controlled fall defines bipedal locomotion in humans. But this efficiency required profound skeletal restructuring. Quadrupeds carry weight directly over their limbs. Bipedalism necessitates a bowl-shaped pelvis for support. The ilium blade shortened and reoriented backward significantly. But this reorientation anchors crucial stabilizing muscles effectively. The hip socket itself deepened to prevent lateral dislocation. But this rigid lower structure became the foundation for upright posture. And now that we understand the pelvis, let's explore the spine. On a primitive, relatively straight spine is inefficient for vertical load. Bipedalism forced the development of crucial spinal curves. The lumbar lordosis, the inward curve of the lower back. This curve shifts the body's center of gravity directly over the hips. The cervical curve balances the head weight directly over the trunk. Think of the spine as a spring system, not a rigid rod. The discs act as shock absorbers across these critical angles. This S shape is the hydraulic engine for sustained upright movement. The transition point where the spine meets the pelvis is vital. A weight flows down through the spine, through the pelvis, into the legs. And now that we see the frame, let's examine muscle function. The gluteal muscles, particularly the gluteus medius, are key stabilizers. They prevent the unsupported hip from dropping to the side. Without this, walking becomes a dizzying side-to-side sway. The leg bones must align perfectly beneath this shifted center. The knee acts as a pivot, absorbing initial ground reaction forces. The foot completes the chain, utilizing an arch for spring action. The heel strike, mid-stance, toe off. A complex timing sequence repeats. Every segment must cooperate for energy efficiency over distance. This sophisticated design evolved over millions of years. Early bipedal ancestors exhibited transitional pelvic traits. Their gait was likely less energy efficient than ours today. Crucially, the femur angles inward toward the knee joint. This valgus angle brings the feet directly under the body's mass. Though without this angle, the body would constantly sway side to side wildly. Even the big toe evolved, losing its grasping opposability. It became a rigid lever, essential for the final propulsive push. Every component, from hip to toe, adapted for linear travel. With this, anatomical integration is what distinguishes efficient bipedalism. It's a constant trade-off between stability and maximizing forward momentum. Torso rotation also plays a subtle, yet critical role. But this rotation minimizes the need for excessive hip abduction. And the combined effect keeps the head surprisingly steady above the feet. This entire process requires immense, unconscious neurological coordination. Proprioceptive feedback constantly informs the muscles of ground contact. The fundamental architecture remains, even when we accelerate into a run. And running introduces vertical oscillation, demanding greater spinal compression tolerance. And the deep hip socket provides superior leverage for powerful propulsion. It is a masterpiece of mechanical engineering, sculpted by necessity. The cervical curvature dictates where the eyes look relative to travel. A natural selection favored those structures that conserved precious energy. Fusion in the sacrum creates the necessary rigidity for load transfer. This single leg support phase is the hallmark efficiency of our design. A standing tall opened new sensory perspectives on the savanna. The differences between our hips and those of close relatives are dramatic. These muscular attachments were repurposed for balance, not power. The spinal curves act as tension cables, distributing impact loads evenly. Even the heel fat pad evolved to cushion the initial heavy impact. Every step is a testament to millions of years of skeletal refinement. The mechanics of walking are, fundamentally, the mechanics of survival.